So good afternoon. Welcome to the Oxford Internet Institute. I'm Jonathan Zittrain, one of the people who teaches here, and it is my distinct pleasure to be able to introduce John Wilbanks. I first met John as a fresh-faced, he's still very fresh-faced as you can see, but as a fresh-faced 20-something, when I was running the Berkman Center for Internet and Society at Harvard Law School and hired John as the administrative director. And John did so well at that he was soon plucked away, first by entrepreneurial leanings. He helped found a company called Incremental, and then re-entered the world of internet digital policy by working with Science Commons. And it's sort of suited, I think, because I think of John as somebody who is the consummate catalyst. He helps bring people together and sort out their problems and sort of is a wonderful jack of all trades. So it's my pleasure to introduce John Wilbanks, who I understand will be talking for a bit about what Science Commons is and what it does, and then we'll have an open conversation. And maybe, given our numbers, why don't we do a quick round around the room of just introductions so we know and John knows sort of who's here.
Hi, I'm Matthijs den Beste. I'm a research fellow at the Oxford E-Research Center and an associate to the Oxford Internet Institute. And one of the research interests of me is open science.
Well, my name is Wolf. I'm a first-year DPhil student here at the Oxford Internet Institute, and my research interests circling around the Web 2.0, which is now called Social Web or X.0. So like the whole peer production, peer producing, peer distribution topic, and the impact on intellectual property law.
My name is Julia Gazarian. I'm a visiting student at the Oxford University. I'm more researching the public participation in policy making, and especially through e-petitioning and electronic devices.
My name's Lucy Power. I work for a company called Ingenta, and we do online academic publishing. We run an aggregation for all of these academic publishers, and I'm here just because I'm interested in what John has to say, but also I don't necessarily represent the opinions of my employers today.
But you might. We'll find out afterwards.
We'll find out, yeah.
Does anyone ever?
My name is Max Loebser. I'm a default student here at the Internet Institute, and I'm also interested in peer production and security matters.
I am Terje Rasmussen. I'm normally at the University of Oslo. Right now I'm a visiting scholar here at the Institute.
I'm Jennifer Fry. I'm a research fellow here at the Institute, and I'm also interested in open science.
Sunny Mitra, who I default student, first year, working in ICTs and development.
And Ralph Schroeder, I'm a research fellow here, and I'm also working on e-science and all that kind of thing.
Malte Ziewitz, also DPhil student and just curious.
Jennifer De Beer, a default student here at the OII, but also extended the invitation to John to come, and know John because I was trying to get him to come to South Africa to exert some influence with regard to open access there. Yeah.
John Dixon, Cavisham Research Group. We're an independent group researching and building what we call global information networks hosted on the internet. I've also had some contact with John over another initiative with which he's involved, which is the Global Information Commons Science.
I'm Richard Pointer. I'm a freelance journalist. Taking interest in these things.
Okay. And are we on or off the record for the purposes of any freelance journalists, bloggers, or spies in the room?
We're on the record. I think we're on the record. We're being recorded for the slides.
This is the UK. We have to have this little kabuki theater before we... Okay.
So thanks everyone. I wasn't sure sort of the size of the room, so I have sort of my big room presentation because it's easier to go from the big room one to the smaller room one. So there's a lot of pretty pictures, which I try to use in place of the tyranny of PowerPoint bullets. To sort of set the context, what I wanted to get across today is that modern science has gotten really complex. It's gotten very collaborative, interdisciplinary, technology-driven. And some of the tasks that it's trying to solve appear to be so complex that no single organization can solve them. So things like figuring out what diseases do, how, why, and how to cure them, climate change. And it may well be that incremental innovation across organizations may be the only way to really address these issues, because sort of in any organization there are more smart people outside it than there are inside it, no matter how big or powerful or wealthy that institution is. And so that's the theme I'm going to kind of keep coming back to. And all of this is a prelude to the idea that a commons, which I'm going to try to define, may be a way to address this problem, may be the right way to manage the knowledge that gets created in sciences, and I'm going to focus on human health, in a way that can stimulate more incremental innovation. Now, we don't know this, but it's pretty clear from some of the data we have that the existing approaches are not sufficient the way that we're going. So I like to start with visually talking about and showing the way that science changes. So these are the way we used to look at the sky. This is how we look at the sky now. These generate essentially petabytes of data on a monthly basis. And that's going up exponentially year by year by year. It's happening in the life sciences. So this is how maybe 15 years ago sort of the state of the art of doing biological assays looked. And this is what it looks like today. It keeps getting smaller, faster, and cheaper. And as a result of this, there's a lot more information available than there's ever been available. These are two of the first animals that were sequenced. So the first organisms sequenced, Arabidopsis, which is a milkweed, which was sort of serves the underpinning for agricultural research, and the lab mouse. And as a result of that, this is what has happened to data in the life sciences. This curve is not showing any signs of tailing at this point, because this is just raw sequence information that's in a database called GenBank, which is run by the U.S. government. When the U.S. government spent money to sequence the human genome, which was $3 billion U.S. over a long time period, that went into GenBank, along with, again, mice, rats, monkeys, dogs, and so forth. And the cost of doing this, again, for humans, $3 billion. Within 10 years, that's going to be down to $1,000. And so the total number of sequences, this is just for one sort of perfect human, but if you get to a world where it's only $1,000 to sequence your genome, it's not that much farther till it's the $100 genome, which is the sort of stated goal of the sequencing community. So you'll be able to carry your genome around on a flash drive. And the amount of total data available in terms of raw sequences is going to keep going up if you think about the number of people on Earth. But the genome is sort of just the base point. So this is from the Arabidopsis project. This is the assignment of genes to the raw A's, T's, C's, and G's on the genome. And so this starts to provide some context to genes. Now, this is done in a very collaborative, distributed, peer production manner. There's lots of open source software that does gene finding. It goes and looks for pieces of the genome that appear to represent protein coding. Right? So this is the activation parts of the genome. The software assigns probability. People go in and take a look at that. Maybe they do some experimental work, and then you can assign a gene name, assign some sort of putative function to that gene, and so you get this annotation system to the genome. So if you think back to the last slide, for each of those genomes now, there is annotation and context that's appearing on all of this. And eventually, that turns into papers. Right? So this is sort of very stylized, structured knowledge that represents the output of 2 years of lab work, $1.5 million or £1 million in research that's invested, and that gets boiled down into maybe 6 or 7 pages if you're lucky, a nice long journal article, which is being written basically to convey 1 or 2 key facts and to contextualize those facts into the existing body of knowledge. So this is talking about what certain genes do in rat brains after traumatic brain injury. And this is actually a fairly generic paper compared to a lot of other papers in neuroscience. It's comprehensible to the layperson, much more so than very detailed cell-cell signaling papers, for example. So every fact or asserted fact in science goes through a peer review process and a publication process and turns into something that looks an awful lot like this. Now, this hasn't changed a lot. I'm going to talk about this when I get into the open access part, but the main part of the idea is that the data gets analyzed, gets turned into a paper, and like the explosion in data, we have an explosion in papers. So this is one protein. It's called P53. If it breaks, you tend to get cancer. It's the protein that stops your cells from killing themselves when it breaks. So if P53 is working right and your cells break, they commit suicide and you don't get tumors. If p53 does break, your cells keep growing, and that's essentially what a tumor is. So there's 40,000 papers, 40,800 papers on this one protein in the US database. And that's, on one level, that's really good. We have a lot of facts about this protein. On the other level, that's a lot for anyone to read. There's about 95,000 public data sets associated with the protein as well. And so as a result, the ability to search intelligently is becoming one of the most important parts of modern biology. And so you can spend an awful lot of time in the lab, or you can spend a little bit of time doing full text search on PubMed. But unfortunately, the state of the art for text searching for biological articles is nowhere near as advanced as, say, Amazon or even Google, because scientists write papers, they don't hyperlink to each other. So the PageRank algorithms that make Google so successful don't really work on scientific literature. The best you can do is citation cross-analysis. And then from that, you've got to look at each of these things in context with other things. So this is the protein p53 is in the middle of this. You can see it's sort of in the lower, it's the only one that's in red, and sort of that bar. So this is a biological circuit that governs cell-cell signaling. So each of the nodes in this network have their own forest of information, of papers, of data, of sequences, of annotations associated with it. And the reason that it's so hard to come up with drugs is that perturbing any one piece of this network has side effects throughout the rest of the network. And it's really hard for any one human to keep enough in their head to build an accurate predictive model. Essentially, the folks that work near me at MIT would say it's impossible for any human to hold enough of the information in their head to make an accurate prediction. And it's getting a lot easier. So you can buy DNA sequencers on eBay now. This one's under $500. They ship anywhere in the world. You can buy all the reagents to do the DNA sequencing that you want. This is about a month old, but they seem to be dropping. When I started using this bit in my presentations, they were about $800. And now they're down to about $500 over the last year. And so this is all really good, but what we're trying to do is to come up with crops that feed people and drugs that cure diseases. And we're not. So this is a chart from the pharmaceutical industry. And the gray curve at the bottom is total research and development expenditures by the industry. And so at the far right of the graph, $30 billion was spent in R&D in 2001. Right, so that's an order of magnitude more than it costs to do the entire genome. Was spent in 1 year. And the red dots and the red trend line represent the number of new drug approvals in the United States. And so that line is actually only sort of trending up if you take out what are called Me Too drugs, which is to say the third drug that cures heartburn, or the fourth drug that deals with what we call lifestyle illnesses in the United States. Like my favorite one right now is restless leg syndrome. There's a raft of drugs coming out to treat restless leg syndrome. Your leg shakes at night, keeps you from sleeping. The total number of small molecules has actually gone way down. And that's because we simply don't understand enough about toxicity and side effects to get drugs through the trial process. And the answer has typically been that we need new technologies. We need new machines, we need new robots, we need new software. We need some tool will come along and fix this problem. But there's a growing understanding that the problem itself, right, of dealing with a complex dynamic system like the genome over time, in response to a disease and in response to a drug, is just too complex for a traditional model of collaboration inside one company. And the pharmaceutical companies are starting to get this. They've formed any number of consortia to address these problems. They're actually starting to talk now about even sharing clinical data on failed drugs, because right now, there's one target, which is an arthritis target. 19 drugs have failed clinical trials. So on average, that's about 800 million per failure. And they keep failing for the same reasons over and over and over again. No one shares their information. So it's very easy to go and replicate the failure of someone that's gone before. And so there's a growing movement towards a commons model for incremental innovation. And incremental innovation here means something like open source software. People say open source science or open science. They, in my experience, they're talking about things like patents, like sharing patent licenses. I don't think of it that way. I think of open science as very much like open source software, which is that someone needs to write a driver for a card. They write the driver for the card, but it becomes part of the distribution. Whereas in science right now, there's a real, especially in biology, there's a real social and cultural pressure to keep whatever you come up with private to yourself, so that you get tenure, so that you get the next article, so that you get the next grant. And there's not a culture of contributing even the little stuff. And so patents, at one level, I think are a problem, because they're a problem, especially in agricultural technology, to commercializing the output of the research system. But the way the research system is built right now, we're not even getting enough inventions that can be patented. If we had 19 drugs for malaria that were competing on patents, that would be a lot better than the scenario that we have now, which is that the cost of research, the cost of replicating someone else's work, the cost of discovering things that lots of people all over the world know but aren't talking about, is so high that it's having a cumulative drag on innovation long before you get to patents. And so Science Commons works on those problems. And when we talk about a commons, right, I don't know how familiar everyone here is with CC, so I'm going to kind of burn through this so everyone knows it. My background is with Creative Commons. This is a Creative Commons licensed photograph of a commons in England. What we have from Creative Commons are basically copyright sharing licenses. These are free contracts. They don't cost anything to use. They're not mandatory. You have to own your own copyright and choose to use them. And they're modular, which means that there's a base agreement underneath it and a series of choices that you can make that change the rights and obligations you give to the user of your copyrighted work. And so the core right is that you're free as a user to copy, display, distribute, and perform any copyrighted work under a Creative Commons license. This presentation's under a CC license. Everyone's welcome to copy it and mail it around to people. You can basically do whatever you want with it. But because I'm using stock photography and some fair use things, you're not going to be allowed to make a derivative work out of the core file. So it's going to be under what's called a non-commercial, non-derivatives license. And those are the rights that I reserve as the copyright holder. So that's how the CC licenses work. There's three forms of them. There's the human-readable form, which is intended for non-attorneys to look at. And the key here is to really look at the icons. The icons represent obligations to the user. So by means you've got to give attribution, the $ non-commercial, and the inverted copyright sign means that this particular commons deed represents a viral copyright license, like the GPL. It passes through to the derivative works. There's also a lawyer-readable version of the license, which I won't show, and a machine-readable version of the license, which is rendered in a semantic web language called RDF, which I'll get into this a little bit later. But the main point is that RDF lets you describe things on the internet that are not necessarily on the internet. So things like the idea of reproduction and the idea of derivative works. We can describe and refer to in a way that lets machines comprehend them, which means you can search Flickr, Google, Yahoo, Blip TV. We've got a few more of these now for works that are available based on their terms of use. And so these are licensed on about science. There's about 25,000 Flickr photos tagged with science. Growth pattern of Creative Commons licenses from launch in February. It's actually almost 4 years ago. And this is over the first 2 years. It hit 140 million last summer. We expect that to continue growing exponentially. There's no data that argues against that. Science Commons is a project within Creative Commons. We have, actually this is out of date, I've got more people now. So the people on the far left are staff. So we have counsel and programmers at this point and a project manager. The middle bar are the lawyers and technologists that founded and advise us as we go forward. You may be familiar with Jamie Boyle and Hal Abelson in particular out of that group. And then on the far right is our science board. Josh Lederberg on the top, John Sulston just below, both won Nobel Prizes in physiology and medicine. Sulston most recently, he's actually knighted here in the UK for his work on worm genomes. And he developed the policies that led to the genome sequences being shared in actuality as opposed to in theory. Artie Rai is another attorney. Mike Eisen is a bioinformaticist. And Paul David, who I'm sure many of you know. So some of the people that we work with commercial publishers, non-commercial publishers, database providers, open access and closed access, as well as universities. And all of these slides will be available so you can have them. So when I say a science commons, there's a lot of different things it could be, but for our purposes, we're talking about access to the physical things you need to do science, like mice and DNA. We're talking about the journals that contain sort of the scientific canon, the information that you have to build on to do new science without completely missing someone else's work. The data, and then when in the lower left is sort of a synthesis of all of this. This is mapping of information to data. So this is how you assign genes to sequences and so forth, because there's not really a name for that, but that's inherently what scientists do. And one of the arguments we make at Science Commons is that if you use the net and the web wisely, you can start to allow this to emerge much more incrementally than it currently is allowed to emerge. So we'll start with open access. I like to start by this is the first journal. I like to kind of start by showing this. This is from 1665. So this is the year of the Great Plague. It was the year the red spot was discovered. And this guy, Henry Oldenburg, collected letters from friends of his that were doing interesting things and published them into a journal. And this was as part of the Royal Society in London, essentially. It was an interesting time. So the kind of ideas that survived peer review, one of them was that syphilis cured the plague. So this caused a stampede of certain activities that didn't actually cure the plague. And it sort of provides the argument for peer review in some contexts.
She died happy.
Well, that was the idea. That was the idea. And so this is what the Royal Society looks like now. And unfortunately, the idea of the paper hasn't changed nearly as much as the technology that underlies it. So it's still the idea that you write a letter, except now you write a letter to Nature or to Science or to the Lancet or the British Medical Journal. But you treat it like a letter. And the PDF is really nothing more than a digitization of a letter. It takes no advantage of the multidimensionality of the information in a scientific article or a scientific experiment. So, because it's on the web, the cost of distribution is pretty low, and anyone with a net connection can get to the web page that I'm showing you. Unfortunately, most of the articles are not available without a subscription because they're closed access. This is the beat up the publishers graph. The red line in the middle is the Consumer Price Index in the United States. It represents kind of the average cost of inflation. So how much more expensive things got in the United States from the mid-1980s to about 2 years ago. Whereas the top two lines are the cost of scholarly journals. And the output of this is that Reed Elsevier, which is one of the largest for-profit publishers in the world, had a profit margin that was between Pfizer and Microsoft last year. Right? And now they don't write the articles, and they don't peer review the articles. Right? Scientists write, and scientists peer review. This is the cost of publication and distribution. And so despite the fact that in every other industry the cost of publication and distribution has dropped with the internet, apparently the cost of publication and distribution has increased in scholarly publishing as a result of the net. Now, this has put a lot of pressure on research libraries in particular. Library budgets haven't gone up 6 times the cost of living during this time period. And the reaction has been something that's called open access, and so typically represented as an open lock by most folks. And what it is a movement that talks about the rights of humanity to access the fruits of scientific research. And so this is the definition that I like. It's from the Budapest Open Access Initiative, which was funded by the Soros folks. And so the open access definition is that users are free to read, download, copy, distribute, print, search, or link to the full text. If you go back to that slide about the P53 protein, 40,800 papers, only about 10,000 of them are available under full text. And that's actually a really good percentage. Most of the time you get 2 paragraphs out of a 6-page paper that are publicly available. And the only constraint and the only role of copyright is to give authors control over the integrity of their work and the right to be acknowledged or cited. So the Budapest definition actually has its 5-year birthday next week on February 14th. And one of the reasons I like that is if you look at the Creative Commons deed, basically the attribution license implements the Open Access Initiative. Almost word for word. It's strange that they weren't designed this way, but it works out pretty nicely. And what you have here is a case where you have a policy or a philosophy and you have a free legal implementation. In a lot of cases, it's very difficult to implement a philosophy of openness or sharing if you don't have the legal tools available, because most of the people that share this philosophy don't have the money to pay lawyers to figure out how to give it away. Now, there's been a very serious attack in the United States by the publishing industry on this whole idea. And Nature Publishing Group actually broke a very brave story about a week and a half ago about the engagement by the American Association of Publishers of a lobbying group that is most famous for defending a couple of disgraced CEOs in the United States. And this was the recommended meme by the PR firm to fight the open access movement, which is that public access equals government censorship. Right. There's some even more Orwellian comments that I'm not going to come into, but this is my favorite one. And so this is the best argument that can be marshaled against public access, is that by forcing journals to give the copies away, that would somehow equal government censorship. And the recommendation is to repeat this over and over again until everyone believes it. And in the United States, that has worked sometimes. The argument underneath this is that public access will kill peer review. And that's, in effect, creating government censorship. Now, the Public Library of Science Biology Journal, one of our founders is one of the founders of this journal. PLOS Biology is currently the #1 ranked journal of biology in the world, according to the traditional industry-based impact factor settings. Despite the fact that all of their articles and images and data are under a Creative Commons license, it still is somehow managing not to kill peer review or quality or be government censored. And Springer lets you actually purchase the rights to apply a Creative Commons license to your work at the moment that you submit. And the cost is $3,000. That's the cost of processing and formatting and printing your article to Springer, which is, again, 6 times the cost of a DNA sequencer, is the cost, apparently, of your copyrights. So, context. Now, the NeuroCommons experiment is what we're doing at Science Commons. It's an attempt to actually implement a lot of this stuff whole, to deal with materials, to deal with data, to deal with papers, and to look at new ways of mapping all that information into a unified system to see whether or not this actually does make science more efficient. One of our sort of guiding principles is to try to generate data. It's very easy to talk about a commons. If you go to conferences about open science, the word commons is thrown around so much that I think it's actually in very real danger of being degraded. People write software that searches the web and they say they've built a commons. One of the quotes I heard was, if you'd have a sandwich that no one wants to eat, you can sprinkle some commons on it and feed it to the funding agencies these days. So we're trying to do something that's a little different. So we're working with a series of funders of basic research. So in the brain in particular, there are a lot of rare diseases, rare being defined as not enough people to make it financially interesting for a pharmaceutical company to discover a drug. Now, Huntington's disease is sort of the archetype here. Huntington sufferers, I think, number something like 25,000 a year. It's not anywhere near enough for the pharmas to go after it. But there are a lot of people that have autism. There are a lot of people that have Alzheimer's disease. And multiple sclerosis sort of suffers the same problem as Huntington's. But they're all looking at the brain. They're all looking at the same cells, the same tissues, the same pathways. But what they're creating is essentially silos of all of the knowledge, represented as materials, represented as papers, represented as data, that really, in vivo, is interconnected. It's only being disconnected by policy. And because the funders control, right, the funders put the money in, they have the right to dictate the terms on which things come out of the funding, we're able to talk about building a contractually constructed area in which there is, from the beginning, a regime of some rights reserved sharing of materials, data, and papers. And the idea is to enable, really, the movement from basic research into a meaningful discovery, not another paper that generates another fact, however important that fact may be, but the ability to actually turn that into a drug. And so if you want to visualize it, we want to put all of these things into a contract zone that treats them at some sort of pre-competitive level so that the scientist who's working on Alzheimer's can access the content from the scientist working on autism, the scientist working on Huntington's, the scientist working on Parkinson's. Because the idea is that in all likelihood, the incremental innovations of every scientist working on the brain will lead to any one of the diseases being cured. Now, this all sounds great, right? But scientists in biology don't like to share. You know, there's a long tradition. Everyone talks about Newton and standing on the shoulders of giants. You know, that was an insult that Newton leveled at Robert Hooke, who was a short man and a competitor of his. And it has been sort of reworked now to talk about this stylized ideal of scientific sharing, and it's not true. This is a study published in the Journal of the American Medical Association on data withholding and materials withholding. It's really bad. Something like a fifth of published research cannot even be tested because of withholding. And there's some evidence that less than half of published research could be validated at all because of the selection process by which you choose data and game to get into certain journals. But the key conclusion is that the free and open sharing is not just of information, but information, data, and materials, and that it's breached on a daily basis. So when I talk about materials, you know, mice are one thing, but mice tend to be patented. Mice and organisms, anything that's sort of complex and multicellular, tends to have a patent, tends to have some financial value. But the vast majority of knowledge in science is this stuff. It's little bits of DNA. And it's usually not patented because it's usually not worth spending the money to go through the patent process to get at it. So this stuff just gets withheld. Economists would call it a club good. You know, I would mail it to Jonathan here because he's at Oxford, and I might get a nice partnership out of Oxford. But if I get a request from Brazil or from South Africa or from China or from India, I'm probably not going to task a postdoctoral student to spend 5 days manufacturing a copy of the tool and mail it. I'm certainly not going to deal with the contracts and the export restrictions. And it creates a network effect that basically says if you're at MIT, if you're at Oxford, you can do meaningful scientific research. If you're not, it's very difficult. And there's no patents doing this. This is just science culture. So we're contract people. We take a contract approach, and the contracts here are called materials transfer agreements, or MTAs. I try to define my three-letter acronyms. And the problem is that there's a lot of this stuff. There's a lot of materials that need to move around. There's a very high transaction cost. As I said, you have to manufacture it. It's not digital. It's not rivalrous. I can make you a copy, and you can have it just as much as I have it. But there's a cost of manufacture and shipment. It's a low priority, right? Because I'm helping you do research. I'm not helping me do research on a day-to-day basis. And there is, again, competition and deliberate withholding. And it means that it's really slow. I mean, an average materials acquisition process, unless you're in the club, appears to be anywhere from 6 to 12 months. So you read a paper and you say, wow, I'd like to build something on that. 6 to 12 months later, you can do the work, if you're lucky, if you get the material at all. And that, you know, we really don't know what the cost of that is. It's very hard to calculate the opportunity cost. There's an attempt to address this. This is the Uniform Biological Materials Transfer Agreement. 250 institutions worldwide have signed it. And in theory, it creates a wonderful regime in which things move around. But, you know, there's a saying in the United States that is attributed to Henry Ford that I'll give you a car in any color you want as long as it's black. And that's pretty much the UBMTA. The signatories are free to depart from it, and they do. They edit it, and as any lawyer who's done transactions will tell you, the minute a contract gets edited, the whole thing has to be completely reviewed. You might as well not have a standard agreement. So we're trying to create a standard transaction regime. We're working with, again, these funders in neuroscience to mandate its use so that scientists don't have the choice. Well, basically, they answer a small set of questions. They said, you know, is there a field of use? Are you allowed to make copies of it? Right? That'll give you a lot of information about whether or not you're allowed to distribute it. Duration of use, are you allowed to keep a copy of the material at the end, and is this going to be for published research? And that'll generate a commons deed, very much like the Creative Commons licenses, which has some core information associated with it. So this one would be, you can use this for academic but not for commercial purposes, and you're not allowed to distribute the materials to anyone else. So there's two ways to use it. One is, like a Creative Commons license, is a public offer, sort of a one-to-many, which says anyone who wants to sign this contract gets a copy of the material. And the other is to simply list the material as available under the system, which eliminates sort of inherent imbalances in power between someone who's got 100 lawyers, like Pfizer or Novartis, and someone who doesn't have any lawyers at all. Because you're dealing with totally standard language. There's no way for drafting to create a power imbalance. There will be a machine-readable version of it. This is the draft metadata. If anyone sees this on the web, this is draft metadata. It should be done in a couple of weeks. And what you see is, again, sort of like the Creative Commons metadata. The last two lines, first word on the left, last words on the right, this permits scaling up and it permits retention, this particular version. And that will let you use Google to look for materials that are freely available under these kind of licenses. So it solves the problem of finding the tools. It lets you do things like link the tools into the papers where they're described. It lets you find them while you're looking at databases. You can integrate with other systems. These are ontologies of medical terms, and say, find me all the materials that are available for a certain disease. You might actually want to make certain tools available for WHO global priority diseases, but reserve the rights for cancer.
Just this question, I mean, so what kind of materials are we talking about? Are we talking about, I give you a vial containing my genes, and that can be in some way, at a cost though, copied. And you're saying that apart from shipping and handling, as you might say in American TV terms, it's yours, and you're free to copy it as long as it stays within this zone that you've described. Is that the kind of materials? Is there other, are these also molecular compounds that could be used for drugs, or is this, blood or other substances?
We're mainly dealing with replicable stuff at this point, so biologics, DNA, animals, cell lines, etc. And so there's a growing network of fulfillment organizations. So this is a screen grab from an organization called AdGene. They're a nonprofit organization that exists to take in copies of DNA plasmids and store them. And their business model as a nonprofit is that if someone calls to get one of those tools, they make a copy and they send it out and they charge you the cost of manufacture and distribution, shipping and handling, plus a 5% management fee, which helps them do more of this. And so they're actually one of our partners. You can see at the very bottom, terms and licenses MTA. The best they can do is declare that an MTA exists for it at the moment. And they actually have to deal at this point with something like 500 variations on that standard materials transfer agreement, almost all of which implement the same ideas, the same variations and modifications. And so we've tried to capture most of those in our suite to standardize them. But the goal, and I'm going to get to this, the goal of this is actually not so much to worry about our contracts, is to build a transaction system that makes it easy for the materials to be listed in databases, in papers, in Google, wherever, and to be located in these fulfillment organizations instead of going from scientist to scientist. Because if we're successful at what we're doing here, we're going to create a huge demand for tools, but it doesn't by itself solve the problem of high fulfillment cost. And so we've had to build a pretty significant partnership group. Just as a data point, these are the kind of icons we're looking at, right? Manufacture, distribution, academic use. Again, the idea is to give scientists a voice in the negotiation process, and the icons have been real successful at Creative Commons in giving non-lawyers an understanding of some key rights and copyright. And you can start to track the relationships between materials. Oh, this didn't render correctly at all. So one of the nice things about the way the CC licenses work is that you can have catalogs come online and ask each other questions to see if the listings are the same from one repository to the next. It actually lets you track derived works, because in many cases a scientist will modify the DNA or the mouse or the cell line. And you need to be able to track sort of the flow of a resource through the experiment cycle. And right now that's pretty much completely impossible. But the long-term idea is this, which is that you have providers and recipients, which are both laboratories, which are scientists, and they sign in a materials transfer agreement between them, like a Creative Commons license. And there's a depository institution, so that when the provider creates a material, it puts the material into a depository, and the recipient actually receives that from the depository. Then you get tracking, you get searching and ordering, you get this nice transaction system. And if you look at this and abstract out the ideas, this is basically e-commerce. This is really nothing new. But this is trying to create an e-commerce system for an inherently or currently non-commercial good. And you see, this works for books, for example. I use Amazon all the time to find used books in the United States. Right? Amazon, in this case, would be the provider. They have the listings of these things. I make my deals with Amazon, but they're fulfilled by lots of third parties. And it's really a shame that you can do this for books and you can do this for cookware, but you can't do it for vital biological resources created with taxpayer funds. And another way to think about it is that currently these things move around under a random network. You know, something may have to go from A to B to C to D to E to F to G to become available. And if the funders can start building this, you can have the materials move into the hubs of a scale-free network, which is a much more efficient way to get distribution. And it's actually the network of topology under which most e-commerce systems that have been successful operate. The gorilla is competition and deliberate withholding. That's why the key to all of this are the funders of research. Because the funder of research is the only individual player in this that has the incentive to change the system. Because the value of the money they invest in a given piece of research is proportional to the connectivity of the knowledge that gets created and the availability of that knowledge. And what we've learned over 2 years is that if we don't involve funders, we have no chance of any success whatsoever. So, thinking about sort of the outputs of this, let's go back to P53. 40,800 papers, a paper a day. It's 111 years to read all the available papers. And that's if no new papers get published. And on average, 10 a day get published on this one protein. These are the databases that you're supposed to look at that are involved in brain disease. Right, so that P53 is...
When you say published, do you mean journal articles?
Yeah.
Or
Peer-reviewed journal articles indexed in PubMed.
Right, okay.
Yeah. Yeah, and this is just running some analytics on the PubMed system. Yeah, 10 a day on average. And this is at the top end, right? There's a classic sort of cheesy long tail of how popular certain molecules are to be published on. And this is definitely, Britney Spears of the genome. But it's still, 111 years is a lot of time, and no matter what you're doing in certain networks, you've got to cross this particular molecule. It's a cancer molecule, but it's also really active in Huntington's disease, which is one of the diseases that we work on. And so to correlate that, you've got to look at about 150 different databases on brains. This is a small set of the listing that you need to look at. And I actually stole this from a friend of mine who said that this is the equivalent of what we know about the brain. This is from an old map where they say, "Here there be dragons." Right? And that's about as accurate as our current understanding of the brain is. We don't understand why the brain breaks. We don't know how to get drugs across the blood-brain barrier very effectively. The clinical trial design for things that are involved in psychological disorders are more art than science. We really don't know a lot. We have a lot of content, but we don't know an awful lot. And one of the arguments that we're making in the Neurocommons is that the article as PDF is a really outdated idea, and you need to be able to decompose that if we're going to assemble the information that can let us attack what we know about the brain. The other problem is that the brain, because of the blood-brain barrier, it's not an attractive commercial target. It's not like cancer or, in the United States, obesity. Right? Everyone's going after obesity in the United States because, basically the kids that are growing up in the United States right now are pretty fat as a result of lots of things. But there's no pressure in neuroscience, and as a result, there's actually a little more room for collaboration in neuroscience, which is one of the other reasons we've chosen it. So we're trying an experiment tied with the materials transfer work to decompose articles into text and data and graphics and all of this stuff, and to republish it in different languages, web languages, that make it easier to machine. So here's an example of kind of a classic scientific sentence in the box, right? So CEBP beta expression is upregulated by inflammatory stimulus. Just kind of pull that. So you could rewrite that in a very basic subject-verb-object format. Right? And we actually do this. There's a semantic web language called RDF, which I mentioned earlier, which allows you to do this. There's all sorts of very difficult stuff that goes on underneath this that I'm not going to deal with. We can talk about that in questions if you want. We run software over these kind of articles to extract these facts. We recover the names, the nouns, essentially, and we get the relationship, the verbs, right? And you can also take it down to sort of this thing just occurs with that thing.
This is screen scraping.
This is actually natural language processing and text mining. And these are the outputs that you get. It's imperfect. The top one is from one piece of software. It gets that thing is related to thing, and it identifies the names of the things, right? But it doesn't know what's related between them. The bottom one gets the names of the things and gets that the interaction is an upregulation, but it reverses it. So in this case, it says starvation causes hunger, right? It's imperfect. Publishers should be publishing directly into this format because recovering this from PDF is miserable. But if you get it, you can draw it in sort of a bubble graph format. You can make it directional. So we say, all right, well, this is inflammation down here in the yellow. This is the URL from the United States government that describes inflammation in an ontology. And in the upper right, we have the URL from the database that I showed you earlier. That's the name of the gene involved. And we have had to create, at Science Commons, our own URLs for the verbs, unfortunately, because they just don't exist. Mainly because scientists can't agree on what a gene is, much less what it means to say activates expression of. And if you got this, you could take all of the facts from all of the papers around inflammation, and because they shared a common unique name, right, the common URL, they would automatically come together. And you wouldn't have to do text-based searching. You wouldn't do keyword-based searching to do this. Now, this is really not that easy to do. Text mining is inherently inaccurate and lousy, but it's unfortunately the best we've got. And pharmaceutical companies are spending a lot of money on this kind of stuff, and there are maybe 8 or 9 startups that provide this service to the pharmaceutical industry. None of them make any of their stuff open or public, so we basically went out and bought software from 3 of them so that we can cross-reference the results out of the 3 of them and correct for the biases of each of the different kinds of text mining software. And we generate this kind of stuff out of the open neuroscience literature, which is about, at this point, 1.8 million abstracts reference neuroscience, of which about 900,000 of them are actually articles that deal with neuroscience. We've been able to get about a half a gig of this kind of annotation out. And we're going to be actually publishing this on Wednesday. I have it on my jump drive if anyone wants to take it here, for any Semantic Web hackers. The problem is that we can only run on the abstracts. This is the contract, for example, that Elsevier makes you sign when you buy access to all of the content that they publish. And it specifically forbids you from doing what we've just done. You're not allowed to continuously crawl or index any content published by Elsevier. And in fact, you are subject to enormous financial penalties if you let someone like me do it. They do that with DRM. They actually catch you if you're doing this. They have spiders and robots that are very accurate and very effective at noticing you spidering their content. They also actually encrypt the clickstream. So if you run the medical library at Harvard, for example, you cannot do traffic analysis of what articles your faculty are reading. And I think it's 128-bit encryption on the clickstream. So if you sort of go back to open access, I've plotted a different piece of this. It's also the right to crawl this stuff for indexing and to pass the literature as data to software. When you have that much information, right, the literature has to be treated as a data source, and copyrights block that. So when we talk about the Neurocommons, it really does pull together the literature and the materials and the data, because if you can do this kind of semantic web crawling, the point is that you can use it to automatically index high-throughput data sets. You can look at gene chips now that profile 25,000 genes simultaneously. It is almost impossible to cluster those into something that's meaningful and figure out, oh, actually what's happening here is the ribosome's gone crazy, which is what scientists like to do. And the whole point of doing the semantic web work is to allow computers to automatically assign some sort of context to high-throughput data sets. And then to make sure that the outputs of that come back online and the tools that you need to test the hypotheses that ensue are available. It's really a very basic idea. But at every point there's either a cultural control or a legal control or a technical control or a policy control or just a simple lack of desire to share that added up make it really hard to get to anything that resembles open science. So I'm going to kind of, to beat my point into the ground, right? Some of these tasks are too complex, require incremental innovation, and it may well be best served by a commons approach. So to sort of end, I like to end by talking about sort of where this goes, because all of the stuff we've talked about in terms of acceleration is happening. So this is an ad for biological hackers at MIT. That's a photograph of the phrase "Hello World," which was programmed into a lawn of bacteria. So they were programmed using standard parts downloaded from an MIT database, right? A's, T's, C's, and G's, written as object code, instantiated in vivo, that turned these bacteria into photographic film. And they could take the picture, hello world. This is where they are now. Right? So this is proof of intelligent design, right? A less kind of goofy instantiation of this. This is a programmed arsenic detector, which will turn bacteria into in vivo arsenic detectors. You could drop essentially a little gel cap into a bucket of well water in India. And based on the color of the well water, you would know whether or not the arsenic levels in there were dangerous. And by the shade of the color, like how far along the spectrum they were. So this is sort of the future of incremental innovation in science. Or this was designed by a team of undergraduates at the University of Edinburgh as part of a competition at MIT. If we don't start dealing with some of these issues, right, in sort of regular science, they're going to be completely outstripped by the better, faster, cheaper development cycle of technology. So to prove my point, I got this from my niece. This is a DNA Explorer kit. It extracts DNA. You can actually buy this. It's in the SkyMall catalogs now. I just noticed that on my flight over this time.
This was for use by kids and pets.
Yeah. Okay. And yeah, the age restriction is now ages 10 and up. That's it. Thanks.
Thank you. Questions? Lucy.
Yeah, one of the things you said was that key to the whole concept is getting the funders of the research to cooperate.
Mm-hmm.
I'm curious how you managed to talk them into that, and also whether or not you think that would be possible with the big profit areas of biological sciences.
I think that 5 years ago it would have been nearly impossible. But in this case, the funders of the brain research came to us.
Right.
Because they don't want to spend their time or their money on lawyers. And each of the individual foundations wants to cure a single disease. And they don't really care how they get to that. And that's really a unique motivation in the life sciences compared to a pharmaceutical company whose goal is to return value to shareholders.
Yeah.
So we've had pretty easy sailing with the individual funders of disease. And if you look at the Wellcome Trust here in the UK, there's just a growing understanding that the value of the money they put in has a correlation of some sort to the amount of sharing that comes out. There's a lot of argument over what that value is, what is the exact correlation, but we haven't had to make the argument to most of the funders that this is important. The governments have sort of come to understand this as well. There's a lot of argument now about implementation. And so what we're arguing is that the Commons approach is the right implementation of a sharing methodology. The pharmaceutical companies, they're in a lot of pain. Pfizer just cut 10% of their workforce. Novartis just cut 5% of their workforce. They're calling it the patent black hole is approaching with something like 38%, I think it's 38 or 40% of all of the drugs that are on the market are going to lose their patent protection in the next several years. Something has to give. And we actually have been approached by 3 pharmas and a biotech to help them build what they want to call it a tox commons, where they pool their preclinical failure data on a non-competitive basis, because they don't sell the data to people, they sell drugs to people. And if they can share their data and the compounds are patented, right, the small molecules are patented, they don't lose anything if someone else figures out how the small molecule works. And if they can maybe out of a batch of failures find some standard signals that can be used by the regulatory agencies, that's better for everybody, because at least they know what they have to accomplish. Right now, the feds in the U.S. might fail you because a given liver enzyme was too high in blood work in a clinical trial. Now, they don't know that means that someone would die or get cancer. It might just mean that they're going to get a skin rash. But the problem is we don't know. And so you say, well, that, 50% of the time that means that someone gets cancer. But what if that enzyme goes up nearly every time you perturb the body with a drug? Half of the time it actually wouldn't be causing cancer. And nobody knows. So the people who oppose this the most are the people who sell data. You know, who have proprietary data that they sell as a content business. And the traditional publishers have really fought a lot of this tooth and nail too. But I think that's for different reasons. That's just for basic business model reasons.
John?
Could I go back to the traditional journal publishers, who happen to be my particular bec noir? But from all you've said, there seems to be a very simple solution to the problem, which is cut them out. What function do they serve in this? Because it's perfectly possible. You and I were at a meeting where Martin Hoffman said the science community is perfectly capable of building any system you want, including a completely free open access learned journal publishing system. So why don't you do that? Are you advocating that?
I am not advocating that. I have a personal involvement with a group called Topaz, which is creating a system for PLOS ONE. It's going to be an open source article publishing system. I'm working with you guys on GIXI, which is the Global Information Commons for Science initiative. But I think the role that publishers play is trust. I trust the brand of things that come through science. I trust the brand of things that come through nature. I don't, trust John's Journal of Molecular Biology.
Yes, but
and it's really easy to publish things,
but
right?
That trust has gone, hasn't it? In England, we have the famous paper that linked MMR vaccine with autism, which created a stir, and the Lancet, as a highly trusted journal, have insulated all over the place.
Well,
and the Korean forger was outed, not through all his research had been published in peer-reviewed journals. So the claim by the learned journal publishers that they are the guardians of that peer-reviewed trust mechanism is false. Also because...
But see, the journals didn't do the peer review. The failure was of the scientist participating in the peer review,
yes,
not do the journal.
The journals employ them. The journals select them. There is a career in being a peer reviewer, and what that means is that the old guard get to know poo-poo the ideas of the new guard. But that's a different question.
But I believe that the fraud cases, there's a regular science fraud occurs not because people want to fool the journals, but because people want tenure and want glory and are afraid to take their finger off of the scales. And it's going to happen, and it will be exposed over time as people try to replicate research. But the vast majority of the work that goes on in the journals is actually good work, and it is well peer-reviewed. And I don't see a need to replace that at the moment, because I think you can get a lot farther through self-archiving. I think you can get a lot farther through working with the systems that have evolved.
Yes, but self-archiving enables you to self-publish.
But that gets back to whose work do I trust, and so if it's whether or not the peer review process as it exists is broken is sort of a different point. But the peer review process is the traditional method for assigning trust, and it's worked relatively well over time.
Might it be easier to commit fraud in an open access model anyway? Like, why would moving to that model reduce fraud
I was only raising that in response to John about trust.
Yeah.
But Rob Kling and others in Indiana published a paper years ago about a methodology they call guild publishing, and they pointed out that in the scientific community that had been practiced for donkey's years. JPL share, physicists in particular, share all their research papers, and they trust each other, and that's all done through purely simple to implement electronic means.
So here's the interesting thing about peer review for me.
It's not just about peer review.
But just to kind of follow it on, the model that I think is going to emerge for peer review is being pioneered by a couple of the open access journals, which is to break apart the idea of, is the science valid science, and what's the impact of the science? Because the impact assessment plays into your comments about the old guard, because you respect someone who's already had an impactful survey more than someone who hasn't. But I actually think that open access makes it harder to commit fraud, because it means that more people can validate or invalidate the research. More people have access to it. If it's part of a club that only some people have access to and those people are friends, I think there's actually significant social pressure not to invalidate someone's research. And so PLOS ONE, Biomed Central, these are efforts that are stopping the idea that we're going to judge the impact of research the moment it comes out. Because how do you know? You know? And you start to say, let the impact emerge from the community's usage.
But the other
So
thing
John, let's spread it around a bit. Sorry, John. Let's spread it around a bit. John, sorry. Let's spread it around a bit.
Can I just ask?
Yeah, please. Go ahead.
How you would see the debate about open access developing, because the publishers say it's not financially possible to allow self-archiving, for instance. So do you think that they will just be forced to accept it by government mandate? And that they will find that they were crying wolf?
A lot of the journals claim to support self. There's sort of a forest of different terms and conditions that they impose for that. So some will say that you can only archive PDF. You can't archive PDF. You can only archive in TeX or HTML. You can't put data on. You can. You can do it immediately or 6 months or 12 months after publication. You can put it on your personal website, but not into a database that gets indexed. Right. So it creates an environment where it's just easier not to do it, for the most part. But I have a feeling that's where the publishers are going to wind up sort of arguing and saying, well, you know, fine, make that a piece of the cost of research. Don't make us lower our costs to achieve this. And this is, you know, the author pays or the funder pays model. And that's what the Wellcome Trust has gotten to. And to buy the rights to put things into an XML database where the article is decomposed and usefully available, they've actually had to reserve funds for every paper that gets published out of research they fund.
If you had a few minutes with the Vice Chancellor of Oxford, or name your university president, what would be on your wish list? What do you have a sense of principles or practices that a university operating nominally in the public interest ought to be adopting or encouraging its faculty members to adopt with respect to the practice of science?
I would say first, to sort of declare that part of the mission of the university is not simply the creation of knowledge, but the dissemination of knowledge. So, you know, that's something that a vice chancellor person can say. And I think that's an important element. Second would be to start prioritizing usage of sharing systems. I mean, obviously, I'm going to say, you know, use mine as an example, and I would like in the tenure review process to just ask for the URLs of the full text version of papers. If you published, and there's a citation because when you go to tenure review, here are my papers. Where's the URL to the full text? Right,
By URL, you mean a publicly accessible link to it?
Yeah, exactly. Where can someone who's not at Oxford, right, get the full text of that paper?
And if I can't produce it, it's as if I never wrote it?
That's I think actually you leave that up to everyone. Somebody just ask.
I'm asking your advice.
Well, I think it's not as if you've never written it, because maybe you had no choice, right? Maybe you only had one journal. It's a society journal that only has 2,000 subscribers. It has to sell. It has to maintain a closed model. I mean, it's not. It'd be very fun and pleasant to have a one-size-fits-all model, but it's not. So I think you have to look at those on a case-by-case basis. But if you ask for them, right, if there was an absence every time, right, then that would be sort of indicative. Because then you create the special says, well, Oxford needs an institutional repository. It needs a database for Oxford papers, so that there's a place for these things to go. Right? And that stuff is free. There's a lot of free technology out there to do that. It's not a technical problem. But the university has to prioritize it. Make sure that the librarians have some input in how they put it together. I think the second would be how many papers have resulted from the work that you have created yourself. Right? Not just how many citations, but how many papers have come out of your data? How many papers have come out of the tools that you created? And this is not just biology, right? Anthropologists have to share bones. Physicists have to share access to tools and materials. And so, what is the reverberation of your research within the community? Because again, that's the simplest way to create sort of a market for sharing. And when I talk to the high-level folks at universities, I try to get them to create a market. It says, if I want tenure, sharing will help me get tenure. And then people will find innovative ways to share that I've never thought of if that happens.
And I guess that's different from sharing patent revenue. If somebody at the university invents a really cool thing or a new kind of mouse that gets cancer, so we'll patent that. But you would think that's not something a university should do?
Well, I have a bias, which is that I think that the patent system works a lot better than all of the other systems in science. That's not to say I think it works well, but I think it's working a lot closer to its intended functionality than a lot of the other systems. And there's this rash of gene patents and tool patents. It doesn't seem to be really blocking lots of research. It has a lot of impacts on commercializing that research. But the people that have the money to commercialize pharmaceutical research have the money to negotiate those systems. It's a very real problem in agriculture. I sort of delineate those two. I mean, patents are a real problem in getting crops to the developing world. And there's a group in Australia that's doing fantastic work called Cambia, C-A-M-B-I-A, that I would recommend you guys look at.
And have you looked at their license, which is similar to the sort of thing you're doing, but
well, it's a viral open patent license, yeah. And they've got a lot of licensees on that, but it's very tempting to apply the commons to everything, but the commons doesn't really work that well when the resources that would go into a commons are very expensive and intentionally acquired. You know, commons works well for copyrights because they sort of come down from God when you lift your hand from the paper, right? But you got to go spend money to get a patent. You got to fight for 2 or 3 years to get a patent. You're not that likely to immediately turn around and waive it. And so there's different solutions being pursued at the patent level. Part of what I'm trying to argue is that since there's only one metric of value in the system, which is typically patents, people go get patents they don't need to get because they can't track their impact any other way. And if we can, you know, part of the reason for metadata in this is to find new ways to show impact at the university level. But I would love to move the problem to a patent problem, right? Because then I think we can deal with the patent problem. But that'd be much closer to things benefiting human beings than, you know, just the research system being so inefficient.
Ralph.
Yeah, two-parter, if I may. I mean, the first thing is I want to know a little bit more. You said at the end that one of the biggest obstacles are these data proprietors. And we do have models in publishing even where, you know, the data that sits at the back of an article is also made freely available. So who are those kind of entities, apart from pharmaceutical companies and their kind of subsidiaries or smaller companies that do that? But the second and larger question, if I may, is another one, which is that, you know, obviously a lot of people in this room are sympathetic to this effort and so on. But, you know, if you could zoom out from a sociological perspective, the way in which conflict looks. Conflict works by a lot of, you know, forces converging or focusing on a single point. And I mean, my sense from what you presented is that, you know, there's a very strong network of groups that are pushing towards this. And if you can just, I don't know if you can do this, but if you can kind of impersonally zoom out from your own role, as it were, where would you see the other side? Where are the strongest forces there? Because, I mean, we've heard publishing, we've heard pharmaceutical companies. You know, where's the biggest push from that side coming? Or is it, you know, something like a difference in publics, you know, who say taxpayers' money is spent this way, we should get something back, or rather, you know, market forces should work, in which case the arguments by the pharma companies that intellectual property works by, you know, being protected and so on. Where do you see that other side in rank order of strength, if you can manage it? That's tall order.
Let's keep this in my head. This is an MIT style question.
Sorry.
To the first part, the data proprietors. So there was, you know, Celera Genomics, who was, you know, racing to sequence the human genome because they were going to sell the genome to people. And the argument, and this is the modern one, would be the American Chemical Society, which is spending an enormous amount of time and money in the United States government to try to kill this database called PubChem, on the idea that it represents unfair government competition. You know, creating a database of what drugs do to tissues is unfair government competition to a non-profit organization, which is the American Chemical Society. They spent like $2 million trying to defund PubChem, which was more than PubChem's annual budget.
But it's what the president But yeah.
Well, and it threatens a major revenue stream, and so I'm not really worried about the data proprietors winning that battle. You know, if that was going to happen, that would have happened on PubChem already. I mean, the political environment was not favorable to government-style initiatives. It was very favorable to private industry, and you know, even then, the database couldn't be killed because it was really valuable, and a lot of people couldn't afford the private product. And at the end, this was public research. This was taxpayer-funded research. So I think that's sort of, you know, that's running downhill at this point. To the larger question, you know, not all IP is the same. And so there are traditional publishers which are lined up sort of in lockstep against open access because it threatens their revenue models. They are joined, in many cases, by very small society publishers who have very small publication runs, who desperately need the revenues to support just basic annual meetings. You know, if you zoom out into, say, social science, you know, a lot of those journals have almost no readers, and they need every subscription they can get. So it's this very sort of strange alliance. But there's also sort of an understanding there, at least in my experience, that again, open access is coming in one way or another, and they need to figure out a way to live with it that's as conducive to their survival as possible. And I think that we're going to wind up with something like 6 to 12 months delays before the full XML hits out. And publishers will start to do things like sell metadata and sell ontologies, and sell, you know, pre-formatted and text-mined services, and, you know, stable namespaces, all of which are great. Those are really cool. Those are value adds. Those don't represent sort of marking up and selling someone else's work. Right? I think that's all really good. And Elsevier is moving this way. For example, Elsevier, I know, is selling ontologies to pharmaceutical companies that basically make it easy to text mine articles. So I think that's sort of natural. And if you think about sort of the overall structure of this, you know, one of the most surprising things is how little opposition to these ideas we run into. I mean, I keep waiting for the giant boot to crush us, right? But yeah, it's a measure of how dire the problem is, and how many technologies have failed to provide the savior role. Because first it was going to be combinatorial chemistry, you know, because we have 2 million small molecules that we can test against the entire genome, we're going to find all the drugs we need, right? That was the first one. And then it was, okay, high throughput screening. We can run 2 million of those drugs in a day, right? And didn't work. Microarrays, right? Expression profiling. We can look at the entire human genome responding in real time to a drug. No, you know, they're going down. The numbers are going down. I mean, there's an understanding that it's not a technology problem anymore. Bioinformatics, right? I was actually part of, I can take some blame for the bioinformatics wave, because I actually thought that computers could fix the problem. And, you know, I don't think any one thing can fix the problem anymore. I think it has to be a situation in which every time a contribution gets made, every time a little fact gets established, it becomes part of the canon, and it becomes something that can be easily used. Because then the competition in the pharma industry becomes, you know, who has the best compound? And they would love to have that be the competition. You know, because that's what they can, if they have a compound, they can patent it and sell it to people for money. You know, but they can't sell the data. And they can't sell the treasure maps that sort of say, you know, because each of them have one piece of the map and say, you know, and one group dies when they hit the mountains, one group dies when they hit the ocean. You know, if they can put that together, you know, maybe they lose on the given compound that they put it together for, but they'll win on the next one. You know, and the more drugs they have in the market, the better off they are. So it's, you know, there's inertia that's a problem. There's the individual scientists who hate each other. That's a real problem. But at the macro level, you know, there's a real willingness to look at this.
Matthijs?
I think in research, there's probably, or most of the time, there's a combination of sharing and competition going on.
Right.
So if you take the genome project, people were happy to share the database because they thought they could later compete on the analysis of different parts of the database. aren't you running a risk by focusing on the macro level, on the funders, and on mandating what things should be shared to antagonize the researchers who are actually doing the sharing?
Yeah, we are taking that risk.
And
but the early returns are that as long as you relieve as much of the compliance transaction cost as possible, that the scientist doesn't care that much. Yeah. The reason that materials are a club good is because they take effort to make. If they were simply if they were someplace else, and a researcher in Brazil wanted a copy of it and they could simply put their credit card in and get it, and I never had to deal with it, fine. Especially if I get citations and acknowledgments out of the deal. The thing is, I don't want to think about how to do that. I don't want to think about how to archive my paper. I don't want to have to think about how to archive my data set. I don't want to have to think about how to share my materials. The surveys that have been done are not comprehensive enough for me to be totally comfortable with. But they claim to show anywhere from sort of 1 and 2 to 3 and 4 scientists agreeing with statements like, if my funders said that then I would do that and I wouldn't complain. The blockage points there in many cases are the universities, right? The institutions who think about each of those little bits of DNA as a potential lottery ticket. But they're lottery tickets that someone else would make valuable. And so you put as much control on that individual piece as possible in the event that it becomes valuable in a greater context. Because then when someone wants to get a patent on it, or when someone wants to take it to market, you've got them over a barrel. And so the universities are probably the most, they're probably the most resistant to this. Because there's this cultural idea that no one wants to be known as the person who gave away the winning lottery ticket by sharing it too soon.
At the same time, I mean, the numbers, as I understand them, for the amount of money that universities make, various numbers are cited, but they seem to be universities probably overestimate what they can get by these golden eggs, but that's, I guess, a huge
once in a while you get Google coming around.
Yeah, I think something like half of universities in the United States lose money on technology transfer on a yearly basis.
Jennifer.
Yeah, you've mentioned the role of funders and universities quite explicitly. Do you think there's a role for government, and what would it be?
The governments are the ones who can really make this happen, more than anything. But we have at least found in the United States that there's a real resistance to try new approaches. And there's a very powerful lobby at the publishing side, there's a very powerful lobby on the pharmaceutical side. And the sort of explicit direction we got from government was, go test this privately and then bring it back to us after you've shown that it works. In Europe, it's a very different thing. I've been to HM Treasury 3 times to talk about this. I'm spending most of next week at the European Commission. There's a real understanding in Europe and in the UK that this is an interesting idea. In the US, there's a lot of reasons why this just hasn't gotten a lot of oxygen in the US debates. With the recent changeover in Congress, people are sort of worried about their position in the world and their funding, and they don't want to take chances. So it's been very hard there. Beyond that, I've spent a fair amount of time in Brazil. Brazil is both worried about exploitation of its resources and trying to maximize the value they get from that exploitation. So they've actually passed a law that really encourages patenting of Brazilian resources. They've basically taken all of the aspects of the U.S. legislation that have led to this point and replicated them. So that's an interesting sort of paradox. China and India have been some of the other places that we've talked. China has some cultural issues that make some of this harder. There's a culture of not really questioning the senior scientists that's made it very hard to do some of this work there. India is an interesting case. I think that might be an outcome as well. But that's pretty much 98% of the scientific funding, comes from that set of stakeholders. it's an investment level that very few countries choose to make. You know, and in Africa, I mean, it's pretty much South Africa, and that's it.
You didn't mention Japan.
So I haven't actually. Well, Japan, I've not even been able to get more than one meeting deep in the government in Japan. And there's a lot of reasons for that. I'm not assuming they have anything to do with our ideas. Just we don't even know where to go.
No questions? Yeah, Lucy.
I have one more about you've got RDF that describes your licenses. Do you think the description, like the ontologies and the metadata for the actual research and the topics, is keeping up? You know, is there enough of that? Because that's the key, really, isn't it? Having that all of that described properly and indexed. And, you know, scientists, by and large, are not also computer scientists. They're just scientists, you know, and they're very good at what they're doing, but they don't necessarily can't build an ontology from their own research and stuff like that. So do you see that as a barrier, like, or it'll just lag behind for a while?
There's lots of, well, yes, it's a barrier. You know, asking a scientist to do anything but their science is a barrier, which is one of the reasons why they don't share. But asking them to learn RDF is a non-starter. Asking them to learn HTML is a non-starter. I think that this is a place for publishers. There are lots of point ontologies. I mean, if you need an ontology about yeast signaling, you got one. If you need an ontology of where genes live in cells, you've got one. But they don't connect to each other. They're like intranets that don't connect through any sort of internet. And the things that connect those ontologies are the ideas in the papers. And so that's one of the reasons for the experiment we've got to actually do this text finding, is to see what the value is if you wire together all of these things. And our explicit goal is that publishers take over a lot of the stuff that we're doing, that a Wikipedia model emerges to curate the relationship graph that we're going to create, because what we're creating is very, very flawed. Right? It is using text mining. You know, it's basically three guys at MIT who aren't neuroscientists having the gall to release a big giant graph about neuroscience. But if you think about sort of a lost wax model, you whittle the wax down and you build a mold around it, and then the wax melts out and it gets filled with something that's solid. Right? That's what we hope comes out of this. And so we're working with open access publishers like BMC and Public Library Science. But I think, you know, Nature, for example, is all over this. Nature is one of the most progressive publishers out there. And there's a growing understanding that publishers there's a revenue model here. Right? Some of the profits they're going to lose in open access could come back from selling structured information. And there's a precedent for this. I mean, when the publishers went from print to site licenses, right, for databases to the universities, for a long time, they had this wonderful revenue stream of double licenses, right? Because individual scientists would have subscriptions to a journal, and then the university would have subscriptions to the journal, right? And they lost that revenue after a while. They knew that it was coming. And there's a similar thing happening now, where individual, online subscriptions to Nature or Science are fading in lieu of the site license. And I think that there's a similar migration happening here, and that story came to me from Elsevier. And that's how the guy at Elsevier looked at it. This is natural, it's happening. But new things will come up, because if all of the stuff I've been talking about comes true, what we do is basically create an even larger information problem. And the hardest thing to do will be to find the right information at the right time, to search. And so what I'd like the role of the publishers to turn into is the ability to provide a point of view to the world that's valuable enough, that has access to the validated information. They can make it easy for scientists to get the right information at the right time. Because no matter how much this we automate, it still comes down to a scientist having a hypothesis and exploring it. And that's a role that I think that publishers can fulfill better than anyone.
Much of your description of this has words like fight and enemy and battle in it. And of course, one way in which fights happen is, all right, you try to get government on your side, or you sue, or you board of public opinion, hence the quote you had about public access as government censorship. But another way is sort of the Sun Tzu path of co-opting your enemy. And on that line, I'm curious if you have a view on services like Innocentive. Innocentive is frequently trotted out as sort of a Web 2.0 application where proprietary companies can put out sort of an RFP for independent scientists to take on a problem at 10 or 20K a pop, and they then solve the problem, get their cash, and their solution is completely owned by the company that commissioned it and everything. And it's this odd combination of totally hip and new and collaborative seeming, and also completely in the original proprietary model. And I'm just curious if you have a reaction on that.
I mean, I think it takes a lot of different things to get to the end goal. And I try to be really careful about where I think a commons is appropriate. And and by commons I mean this contractually constructed thing. By science commons I mean the contractually constructed thing that uses Creative Commons methodologies, human readable contracts, RDF, that kind of thing. Innocentive, as far as I know, works really, really well for things like chemical synthesis. I've got a small molecule, I'm a pharmaceutical company, and I've got like a 9-step process to get the required amount of pure chemical out of the synthesis. Put out an RFP, lots of retired chemists and garage chemists can take a whack at it, and it works great. I don't think it works for biology, because not a lot of people, maybe it will in 10 years, that's sort of my point, is that in 10 years that might well work. I don't really have a problem with it. I mean, I'm not inherently against the idea of proprietary stuff. I think if it's paid for with private money, that you have the right to keep it private. I think it's paid for with public money, it ought to be public. I think if it's research instead of commercialization, it's got greater value if it's public. And when I think of sort of enemies and fights, it's interesting that you said I try not to use that phraseology. I guess I use more of it than I thought I did.
You haven't used it saying with you as the subject. You've used it with you as the object.
Okay. But the success that we've had has come by sort of acting as the neutral advocates for science, and saying we had funders and biotech companies and venture capitalists and universities all sit down and help us design our materials transfer system. And none of them brought their lawyers into the room because we acted as the lawyers sort of generally for the group trying to get to a greater good for science. And that's where we've had success. And so when you think about the incentive stuff, I mean, anything that gets us to more meaningful discoveries, I tend to support, as long as it doesn't disadvantage other people. But if you're spending your own money to commission research, you have the right to decide what to do with it. It's my argument is that so much of that comes from our pockets, that making it proprietary or to one company, I think, is a bad investment of public funds. But if Pfizer does it, and they think that's the best way to do it, great. And Innocentive came out of Lilly. It was spun out of Eli Lilly. And the best success story I've heard out of them had to do with the synthesis process that was just bedeviling them. And they got it, the equivalent they got it for was like 3 man-months of burn rate. It was a great deal. It was a great idea. So,
last question, John.
It's more of a comment. But in response to Jonathan's question, you said that the university should treat themselves as not only creating knowledge but disseminating it. I had a conversation with Jan Belterop a little while ago about the crisis in serials publishing, and he actually readily admitted that in the old days the printed journal was the principal means of dissemination of knowledge. And he said the publishers were the disseminators of knowledge, was that written? And he said, well, we haven't been making a very good job of it. So actually some of the publishers may be on that side. And your suggestion that a new role for publishers will be in these other areas is a very creative one. But in that context, everybody's talking about ontologies. And yet Web 2.0, one of the slogans is taxonomy, tagging, not taxonomy.
Right.
And that actually has some very, very important consequences for the idea of your wish, which I'm sure is everybody's wish, to be able to really search the whole of this knowledge archive. And I personally don't think that is eventually going to be done by any form of taxonomy.
Well, I think that, everyone who does this stuff tends to have read and absorbed certain science philosophers, right? So I believe a lot in Kuhn. And structure of scientific revolutions, right? So there are certain things that are sort of dogma, right? You know, we have the central dogma of molecular biology, right? There are core reactions that are very well understood as part of that, which I think can easily be represented as ontology or taxonomy. But every day there are new ideas being proposed and new facts emerging. And so I think that the Web 2.0 tagging world is part and parcel of the day-to-day work of science. But that over time that some of those ideas emerge and harden and can be represented in taxonomy and ontology. But I think the reason that publishers can do this better than, in many cases, individual groups of scientists is I've sat on standards bodies of scientists trying to agree on what a gene is. Right? And it's awful. It's impossible. And so a publisher that can say, well, here's what I say a gene is. And here's a standard vocabulary and sort of names for those things. And that's how we refer to them within this. They publish that schema so that it's available back and integratable with other publishers. That's a really, really valuable service. And then you let the tagging drive things, you know, at the bottom level. But as consensus emerges in the tag world, you can move that up, give it a formal designation. And you let people choose. You know, but I think that, you know, again, if we expected all scientists to agree on ontologies, this would never work. So I think you have to let both happen. I think I think someone's going to get really rich with a company that connects tags to ontologies in an interesting manner.
We've already got the pilot project going.
So, yeah.
John, thank you so much for coming out today. Really appreciate it.